Let's start some important theorem of algebra. Our first theorem is existence theorem of algebra. It states every polynomial equation fx is equal to 0 of degree n greater than is equal to 1 has at least one root, real or imaginary. The proof of this theorem is not required, so we just remember the statement of this result of this theorem, which state every polynomial equation having degree greater than is equal to 1 has at least one root, and that root can be real or imaginary. So our next theorem is every equation fx is equal to 0 of n degree has n roots and no more. Means a polynomial equation whose degree is n, then it has maximum n number of root and it cannot have more than n root. So let's start the proof. For the proof, we will consider a equation of degree n. Let's fx is equal to a naught x to the n plus a1 x to the n minus 1 plus a2 x to the n minus 2 up to so on a n minus 1x plus a n is equal to 0, where a naught, a1, a2, a n, they all are the coefficient of the polynomial of degree n. And as the above theorem states, every polynomial equation of degree n greater than or equal to 1 has at least one root. So it means this equation also have a root, and let us suppose that root be alpha 1. If alpha 1 is a root of this equation, it means x minus alpha 1 is a factor of the equation fx is equal to 0. Means fx is properly divided by x minus alpha 1. So fx can be written as x minus alpha 1 into phi 1x and named it as a equation number 1, where phi 1 is a polynomial in x having degree n minus 1. So it is all because of our fundamental factor theorem. It is because of factor theorem, which state if alpha is a root of the equation fx is equal to 0, then x minus alpha will be the factor of fx, and fx can be written as x minus alpha into some quotient phi 1x, and degree of phi 1 will be lesser than the degree of fx, and that's why it is n minus 1, because degree of fx is n. So that's why degree of phi 1x is n minus 1. Now again same rule will followed by phi 1, as phi 1x is equal to 0 is a polynomial of degree n minus 1. So again by fundamental theorem or existence theorem, this phi 1x also having a root, and let us suppose that that root be alpha 2. It means phi 1x is properly divided by x minus alpha 2, and phi 1x can be written as x minus alpha 2 into phi 2, where again phi 2 is a polynomial in x of the degree n minus 2. So we substitute the value of phi 1, which is x minus alpha 2 into phi 2 into the equation number 1. So equation 1 become fx is equal to x minus alpha 1 into x minus alpha 2 into phi 2x, where phi 2 is a polynomial of the degree n minus 2. Again continuing in the same way, in the same pattern, we will get a point where fx can be written as, after continuing the n steps, we will reach here fx can be written as x minus alpha 1 into x minus alpha 2 into x minus alpha 3 up to so on x minus alpha n into phi nx, where phi nx is a polynomial of degree n minus n. Why it is n minus n? As at the first step in the equation number 1, phi 1 was the degree of n minus 1 at the first step, and after repeating n step it will be n minus n degree. It will be of n minus n degree. So phi nx is a polynomial of degree n minus n, that is of degree 0, means phi nx is a constant polynomial. So we named it as a equation number 3rd. Now equation 3 and equation 3 is the value of fx, and we consider fx as a polynomial in the starting step, so both the values will be equal. So we take both the equations equal, a naught x to the n plus a1 x to the n minus 1 up to so on an is equal to x minus alpha 1 into x minus alpha 2 x minus alpha 3 up to so on x minus alpha n into phi n x, and named it as equation number 4. So in the equation 4 we will compare the coefficient. We'll compare the coefficient of x raised to power n on both sides. So by comparing the coefficient from the left side it is a naught and from the right side it is phi n. It means phi n x is equal to a naught. So phi n x is equal to a naught. By substituting value of phi n in the equation number 3, we will get fx is equal to a naught x minus alpha 1 into x minus alpha 2 up to so on x minus alpha n, and we named it as equation number 5. So equation 5 will represent the value of fx also. Also we know the alpha 1, alpha 2, alpha n, they all are the root of fx, means they all are satisfied equation fx is equal to 0. So alpha 1, alpha 2, alpha n, they all are the root and they satisfy fx is equal to 0, and these all are the n roots. It means fx having n roots. First part of the theorem is proved. In the first part we have to prove that the equation fx is equal to 0 have the n roots. So here we proved in the equation 5 the all alpha 1, alpha 2, alpha n, they all are the root of fx and they are any number, so that's why fx having n roots. For the next part which state it don't have more than n roots, for this if we assign some other value of x in the equation number 5, then the equation 5 not satisfied fx is equal to 0. So that's why the other value other than alpha 1, alpha 2, alpha n, it not satisfy fx is equal to 0, it not vanishes, equation number 5 not vanishes, so it means equation is not satisfied and that value other than x1, x2 and other than alpha 1, alpha 2, alpha n is not the root, and means fx is equal to 0 cannot have more than n roots. So hence we proved here if fx is equal to 0 having the degree n, then it has maximum number of n roots and not more than that. So it's all about the theorem. Thank you.